Today, we're going to continue looking at Taylor series. And recall that we build Taylor series by matching derivatives. We're trying to build a polynomial that has all the same derivatives at a point as the function that we're trying to approximate. So we found some Taylor series already. We looked at e to the x, sine x, and cosine x. E to the x is x to the n over n factorial. Sine x is the alternating odd one. Cosine x is the alternating even one. We had an important realization yesterday. So is that if I want you to find, say, the Taylor series for e to the minus x squared, I can just replace all the x's. I can just compose the minus x squared with the Taylor series for e to the x, rather than taking all the derivatives of e to the x and building it from scratch. So we can just write this as 1, and then I plug in a minus x squared into the x, so it's going to be a minus x squared. And then I put in the negative x squared into the x squared up here, and I'll get a plus x to the 4th over 2 factorial. Then the next one will be minus x to the 6th over 3 factorial, and so on. So this is an important thing to realize, that we can just, if we plug something into a function, we can just plug that thing into the Taylor series for that function. We can just make that composition. This is even better news, not just for finding the Taylor series of these functions without finding all the derivatives, but if you recall, e to the minus x squared is a function that we did not have an antiderivative for. And I said, the way I phrased it was that e to the minus x squared does not have a nice antiderivative. That is, we can't express the antiderivative of e to the minus x squared as a finite combination of elementary functions. But if we allow ourselves an infinite number, an infinite combination, we can use elementary functions. Or we can use just the definite integral. So the antiderivative remember, we didn't have a nice one, but we can write a couple of antiderivatives of e to the x squared. So f of x, the integral, say, from 0 to x of e to the minus t squared dt. We can use a definite integral to approximate our antiderivative of e to the minus x squared. Or we can just find the antiderivative of this series. It can't be expressed as a finite combination of elementary functions, so we'll either use an infinite combination of elementary functions or a non-elementary function. That was an important thing to recognize, that we could just plug stuff in to generate new Taylor series without taking derivatives. Today, we want to find a new Taylor series by taking derivatives. So let's take a look at the binomial series. This is going to be another important Taylor series for us to remember. We want the Taylor series for f of x equals 1 plus x to the p. Oh, near 0. And we're going to do this just by taking derivatives and then plugging in 0. So let's take a look at our function. Our function f of x is going to be 1 plus x to the p. So our function at 0 will just be 1 plus 0, or 1 to the p, which is 1. F prime of x is p times 1 plus x to the p minus 1. So f prime of 0 is p. F double prime at x is p times p minus 1 times 1 plus x to the p minus 2. So our second derivative at 0 is p times p minus 1. Let's do one more and make sure that we've got our pattern going. So the third derivative is going to be p times p minus 1. Those are constants, and I'll multiply by p minus 2 times 1 plus x to the p minus 3. So when I plug in 0, the 1 plus x to the p minus 3, that just becomes 1, and we get p times p minus 1 times p minus 2. So we can see how this is going to go. I'm just going to keep adding. It's like I'm building the factorial, but from the front instead of the back. I'm starting off with p and dropping down instead of starting from 1 and building up. Also, it's different than factorials because p can be whatever we want it to be. So if we continue on this pattern, we can see what the nth derivative is going to be. Actually, I only care about what's going on in the constants. The nth derivative is going to be the first n factors of p factorial. So p minus 1, p minus 2, there's 3 factors. The second derivative is p times p minus 1, there's 2 factors. If I did a fourth derivative, there would have been a p minus 1, a p minus 2, and a p minus 3 when we evaluate at 0. So there's going to be the first n factors of p factorial. So it'll be p times p minus 1 times p minus 2 all the way down to not p minus n, because we don't stop at p minus 3. We stop at p minus n plus 1. A better way to think about this might be to say this is p minus n minus 1. So sometimes it helps to view it as p minus n minus 1. I'm not sure how individually how your minds process things. So maybe you read this as p minus n plus 1 because the third derivative is p minus 3 plus 1, which is p minus 2. Or you start counting at 0, 1, 2, and then we stop at n minus 1. We stop counting. If n is 3, we stop counting at 2, but we start off with 0. So maybe you're looking at this first one as p minus 0, p minus 1, and then stop counting at n minus 1. Or you could be thinking that this is the first n factors of p factorial. All right. So this tells us what we need to build the Taylor series for 1 plus x to the p. So let's build the Taylor series. Immediately, we have to remember what the pattern looks like. So let's see. Let's build the Taylor series approximating f of x equals 1 plus x to the p near x equals 0. So we start off with just 1. I get to 1 plus f prime at 0, which is p, times x. plus f double prime at 0, which is p times p minus 1, over 2 factorial x squared. And then we just have p times p minus 1 times p minus 2 over 3 factorial x cubed, and so on. We can describe this with factorials. Notice that p factorial, I'm just taking off everything after n factorial. So I could read this as p factorial divided by n factorial to get the numerators. But when we use factorial, we're kind of suggesting that p is an integer and p doesn't have to be an integer. So it's 1 and then p times p and p minus 1 over 2 factorial, p minus 1, p minus 2 over 3 factorial, and so on. And so this is the Taylor series for 1 plus x, the p. We could think of this as the series as n goes from 0 to infinity of, to get the coefficient, we'll have p factorial over n factorial. That will pick off the first n factors of p, divided by n factorial. Did I drop something? I feel like I dropped something. X to the n. I think I messed something up. Glad I recorded that. If I had the patience to edit video, I'd edit that out. Because right now, what I care about more is the pattern. Whatever the n factorial, whatever the degree of the term we're looking at, I want that many factors. I want p times p minus 1 times p minus 2 for the 3 factorial. Get rid of this. There we go. So more importantly, let's do an example. Let's suppose that we have a binomial series. Let's suppose I have f of x is 1 over the square roots of 1 plus x. So this is binomial. We got the 1 plus x, and it's being raised to a negative 1/2 power. So it's binomial with p equal to negative 1/2. So let's build the Taylor series. First term is just going to be 1. P is negative 1/2. Then I do p times p minus 1. So I do negative 1/2 times negative 3/2 over 2 factorial x squared. The third degree term is going to be p minus 1 times p minus 2. So negative 1/2, negative 3/2, negative 5/2 over 3 factorial x cubed. So it's very easy to construct a binomial series. So we should clean this up a little bit. So we have 1 minus 1/2 x. See, minus and minus is going to be plus, and I have 3 over 8 x squared. Then see, the 3 is going to cancel out a 3, and so I'll have 5 over 16, and it'll be negative. Any questions? Here are the first four non-zero terms of the Taylor series approximating 1 over the square root of 1 plus x near x equals 0. We can combine this we know that we can use composition to get new series without doing a lot more work, because the goal is to find Taylor series without taking all those derivatives. So if I adjust this to say, instead of being 1 over the square roots of 1 plus x, I replace this with 1 over the square root of 1, say, minus x squared, for secret reasons. I can just take my series for 1 over the square root of 1 plus x and replace all the x's with a minus x squared. I've got the coefficients sorted out. I'm just going to replace all these x's with minus x squareds. So my series, when I simplify, minus and minus is plus 1/2 x squared. The negative gets squared away, so it's still plus 3/8 x to the 4th. And the negative is cubed, but I get multiplied by this negative, so it becomes positive 5/16 x to the 6th, and so on. And in addition to how we can do this composition, we know that we can find derivatives and antiderivatives just a term at a time. So if, for example, I wanted to find the series for g of x, and I don't want to take a bunch of derivatives of, let's say, arcsine x, I can recognize that the derivative of arcsine is 1 over 1 minus x squared. So arcsine is just the antiderivative of 1 dx over the square root of 1 minus x squared. So I can just integrate these terms. So I'll have x plus x cubed over 6 plus x to the 3x to the 5th over 40. And then 70/42 is 112. Is that right? The point is that we want to learn the math so that we don't have to do all those math things. We want to be able to construct a Taylor series without finding all those derivatives, because it's going to be a hassle. Because I'm going to have to use the chain rule, and once I use the chain rule, I have to start using the quotient rule and the chain rule, and the derivatives start getting very messy. So that's going to be your activity in chapter 10. It's going to be about finding some Taylor series. In the beginning, you're going to use derivatives to find Taylor series and look for patterns. But the goal is to just look at a function essentially and say, can I get here from a binomial function? And if the answer is yeah, then we should get there from a binomial function, because implementing a binomial function is pretty straightforward. Also fun would be to find what if the p was an integer, a positive integer? If p is a positive integer, then this process is just going to produce binomial expansions. Don't take my word for it. Use the binomial expansion on an integer power, a positive integer power of the 1 plus x. And you'll just get the binomial expansion. Eventually, one of these factors like p minus n is going to equal 0. And so all the terms will be 0 after that. So that's why it stops. I should let you discover that, but I can't resist exposition. It's weird. When I'm a DM, I don't do any exposition. But in my job, it's just like all exposition all the time. It's like one big voiceover. All right. That's going to do it for today. That's going to do it for this week. Everybody have a nice weekend. I'll see you on Monday, and thanks for playing.